All right, so conditional probability. Famously, there used to be this show called Let's Make a Deal. And it was a game show, and the way it worked, and I think they rebooted it. The rules are different now. But the way it used to work was you'd have three doors, and there was a grand prize behind one of the doors. And so you would choose, and then behind the other two doors, they had like these joke prizes that were like, a goat or something like that. And so you would choose one door. So let's say you chose door number 2. And so then the host, whose name was Monty Hall, would say, okay, here's what I'm going to tell you. It's not behind door number 3. Would you like to change your answer? Would you like to switch which door you choose? And so there was a write up in like Reader's Digest. It was this magazine that had an editorial article called like Ask Annie. And there was a write up about this, and it was like hotly debated among mathematicians. This was relatively recent, not recent for you guys weren't alive, but relatively recent in the grand scheme of things. This was like 1994 when this article was written. And mathematicians were arguing over what the probability of winning was if you decided to change your answer. So if you did decide to change your answer, you would obviously change it to door number 1, right? Because Monty Hall told you it wasn't behind door number 3. So do you think there's a difference? Does it matter if you stick with door number 2 or if you change to door number 1? Or are the probabilities all the same? All right, well, let me ask this question, maybe a little less vague. Let's start over. What's the probability of me, if I just choose door number 2 at the beginning, what's the probability that I win? It's 1/3, right? It's 1 out of 3 doors. I agree. All right. Well, this is where the conditional probability part comes in. What would the probability, if I'm told that it's not behind door number 3, what's the probability that I win if I choose door number 1 after being given the information that it's not behind door number 3? What do you think that probability is? Yeah, you might think 1/2, right? In which case it shouldn't matter if it's 50-50, right? But actually the answer is 2/3. It's much more likely that it's behind door number 1. And so that's what's so counterintuitive about conditional probabilities. Once you're updated on some condition of the sample space, your probability model must update with that condition as well. So I can kind of, let's see, I think I can model for you why this is the case. I think the most intuitive way is this, right? So you have these 3 doors. Whoops. And let's think of all the cases that could be possible. So I'm going to use W for the winning door, and I'll use L for the losing doors, basically, right? So there are only really 3 scenarios that could happen. It could be this, right? Oh, sorry, that. It could be this. Come on. Come on, Wi-Fi. Or it could be this. Okay. So those are basically the 3 scenarios, right? All right. Well, choose a door. Steffi, choose a door. 1, 2, or 3. You say 2? 3. Okay, so let's say Steffi chose 3. If it's the first scenario, if Steffi chose 3, I'm going to show her door number 2, right? I'm Monty Hall. I'm going to show her door number 2. Door number 2 is a loser, right? So if Steffi decides to switch, does she win or does she lose? If she decides to switch, she wins, right? Okay. Let's say it's this scenario. Steffi chose door number 3. I'm going to show her door number 1, right? If she switches, does she win or does she lose? Wins again, right? Because if she switches, she had originally chosen the losing door. If she switches, she wins. And then the final scenario, once again, Steffi chose door number 3. I could show her either one of these. Let's say I show her door number 2. If she switches, does she win or does she lose? Loses. So in how many of those cases did switching enable Steffi to win? 2 out of the 3. Therefore, the probability of winning when you switch doors is 2 out of 3, not 0.5. So extremely counterintuitive, and it was totally debated. And famously, this Harvard mathematician that wrote in about it had been arguing on the wrong side of it. So you can kind of see why conditional probability can be counterintuitive. I'm going to give you another example today of that. And I'll actually do it using an example I had to do for my parents, which was the antibody test. Remember over the summer, there was a lot of talk about the antibody test. Like you could go get tested to see if you had the antibodies and if you were possibly immune to COVID. And the antibody test is said to be 95% effective. But with that in mind, if you test positive for the antibodies, there's only about a 32% chance that you actually have the antibodies. And so we'll be able to compute why that is true today. All right, so let's go over just a few things about conditional probabilities. I'm gonna jump this one, and we're gonna jump just straight to the definition. So I'm gonna have you write down the definition in green and the notation for a conditional probability. So the probability that one event happens given that another event is already known to have happened. That's a conditional probability. So the key word is given that. And the notation we would use is this. So it's just a basic probability notation, but you have this vertical bar. And that vertical bar stands for given that, or under the condition that. So this would be the probability that event B occurs given that event A has occurred. So let's go back to this example. So in 2012, fans at Arizona Diamondbacks home games would win 3 free tacos from Taco Bell if the Diamondbacks scored 6 or more runs. And in the 2012 season, the Diamondbacks won 41 of their 81 home games and gave away free tacos in 30 of their 81 home games. And in 26 of the games, they won and gave away free tacos. We'll let W equal win and T equal free tacos. And we're going to summarize this data in a two-way table. So we'll do win-loss. And I'll do tacos and no tacos. Okay. So let's look here. So they won 41 of their 81 home games. So that's the marginal distribution, right? So 41. Actually, I'm going to do that in a different color. Let's do 41. And we know that the total number of games were 81. So right away, that gives me the ability to say that they must have lost 40, right? Yo, why is my computer so laggy today? Let me switch up the Wi-Fi. Maybe that'll help. All right. What else? They gave away free tacos in 30 of their 81 home games. So tacos 30. That means 51 no tacos. All right, and then we're given a piece of the inside of the table, which is 26 they won and gave away free tacos. So that's that number there. And with that, I should be able to fill out the rest of my table, right? So they have to add up vertically and horizontally. So how many games did they lose but still get free tacos because they scored 6 or more runs? Has to be 4, right? To add up to 30. And then how many did they win but not get free tacos? 41 minus 26, that's going to be 15. And lose and no tacos, that would be 36. Okay, so now let's answer B, C, and D. What's the probability that the Diamondbacks win or there are free tacos? So again, we're going to use our general addition rule here. So we know that they win 41 out of 81. We know that they, with this lag, guys, I'm sorry. I don't know what's going on here. We know that they get free tacos 30 out of the 81 games, but we double counted those games that they won and got free tacos for. So we want to subtract off that overlap, which would be 26 out of 30. So 71 minus 26. No, 26 out of 81, not 26 out of 30. I apologize. So 71 minus 26 is 45 out of 81. All right. Now let's look at some conditional probabilities. Conditional probabilities, as I said, they are counterintuitive, especially when you have to calculate theoretically, like the Monty Hall problem that we just did. But when you're given a two-way table, they're very straightforward to calculate. So all the condition will do in a two-way table is it just narrows what you're looking at. So find the probability that the Diamondbacks win given that there are free tacos. So this just narrows us down to the free tacos as our entire population. We're given that there are free tacos, so we just want to focus on this first column. That's all we care about, is the free taco column. So now, in how many of those do they win? 26. Out of how many are there in which we get free tacos? There are only 30. So the probability there is just 26 out of 30. And then in D, find the probability that there are free tacos given that the Diamondbacks win. So they've swapped the condition in that case. And now we're focused on our given, our condition is that they win. So now we're focused on that first row, the win row, right? And we've just narrowed our population to that. And so how many of those did we get free tacos? There were 26. And out of a total of 41 wins. So 26 out of 41 is our probability for that last one. Great. So no problem when we have a two-way table to calculate conditional probabilities. You just narrow your population to only be the row or column that the condition tells you, right? All right, so now let's talk about how to do conditional probabilities just theoretically. And so here are your formulas. So the probability that event A occurs given that event B has occurred is the probability of A and B divided by the probability of B. And so you can see the bottom one, it's the same thing, but if I swap the order, the probability of event B occurring given that event A has occurred, it's still, the numerator is the same. It's still the probability of event B and event A. But now you're dividing out the probability that event A occurs. So for a conditional probability, you always compute the probability of the events occurring together, and then you divide out the probability of the condition, of the given. I'm going to skip over this one. It's just like the example we just did with the free tacos and Diamondbacks wins. All right, so the general multiplication rule is how to calculate the probability of two events occurring at the same time. So it's the probability that event A occurs times the probability of event B occurring given that event A has already occurred. So in other words, this rule says that for both of two events to occur, the first one must occur, and then given that the first one did occur, the second one must occur. So I'll give you guys an example of how to use these. These are not formulas that need to be memorized. Well, every test is a take-home test right now, so you really don't need to memorize anything. But like on the AP exam, you would be given this on a formula sheet. So you just need to understand the notation. So the general multiplication rule is really useful when we are looking at a sequence of outcomes. And in that case, we can use what's called a tree diagram rather to display the sample space. And so, for example, let's consider flipping a coin twice. That's a sequence of events. We have our first flip and our second flip, right? And the way you create a tree diagram is you create branches for the possible outcomes. So you can see our first thing we're doing is we're tossing the coin. And the possible outcomes, I'll call these nodes. These nodes are either heads or tails. And then you'll label the branch with the probability of that outcome, right? So it's 1/2 and 1/2. And then from each node, you're going to create branches for the outcomes on the second toss. And so from the first toss, you could have heads or tails if the first toss was heads, or you could have heads or tails if the first toss were tails. And then the way you would compute the probability of a certain outcome, so say 2 heads, is you would trace your way through the tree to that outcome. So 2 heads would be, let me get my highlighter here. 2 heads would be this branch right? And what you would do is you multiply the probabilities through the outcome that you traced. So I would just multiply 1/2 times 1/2. So the probability of that specific outcome, 2 heads, is 1/4. All right. So let's try one of these. All right, so Shannon hits the snooze bar on her alarm clock on 60% of school days. If she doesn't hit the snooze bar, there's a 90% probability that she makes it to class. However, if she hits the snooze bar, there's only a 70% probability that she makes it to class on time. And let's represent this with a tree diagram. All right, so here's our tree diagram. There's a sequence of events, okay? So she wakes up and she either hits the snooze bar or doesn't. That's the first event. And the second event is her status in making it to school on time, right? She either gets there on time or doesn't. So I'm going to start my tree diagram with this. I'm just going to say, wake up. All right, my first set of outcomes are snooze and no snooze. All right, she said she hits the snooze on 60% of school days. So that's going to be, I'm going to label this branch with a 0.6, right? And one thing I want you to notice is that between any set of outcomes on any set of branches on the tree, that's a sample space. So the probabilities between those branches have to add up to 1 each time, right? So 1, 1, 1 on every set of branches, right? So with that in mind, what's the probability of no snooze? 0.4. That's it. 0.4. Gosh, with this lag, I'm sorry. I have to restart my computer after this class. All right. And then from each one of these nodes, we're going to go to our next event, which is on-time status at school, right? So if she hits snooze, she could either be on time or late. And if she doesn't hit snooze, she could either be on time or late. All right, we're given some information there. If she doesn't hit the snooze bars, there is a 0.9 probability that she is on time. So that's if she doesn't hit the snooze bar. So that's going to be this branch. That's 0.9, which means she'll be late 0.1 or 10% of the time, right? And then if she does hit the snooze bar, it's only a 0.7 probability that she's on time, which means there's 0.3 that she's late. Great, there's our tree diagram. On a randomly selected day, what is the probability that Shannon is late for school? So this is B. And I just want the probability that she's late. All right. So you have to account for all ways that she could be late. So we're going to be looking at a few different things. There's 2 ways she could be late. She could hit snooze and be late. So that's that branch. Or she could not hit snooze and be late. So that's the bottom branch, right? And so let's calculate each one of these probabilities separately. For this one, multiply through the branches, that's 0.6 times 0.3, which is 0.18. And for the bottom one, that's 0.4 times 0.1, which is 0.04, right? So to calculate the overall probability that she's late, you'll just add those two together, which is going to be 0.18 plus 0.04 or 0.22. It's about a 22% chance that she's late on any given day. All right, last thing, C. Suppose Shannon is late for school. What is the probability that she hits snooze in the morning? So what we're looking for, we're given a condition. We're given that she is late for school, right? So we're looking for this probability. Probability that she snoozed given that she was late. All right. And for this one, we're going to use our theoretical conditional probability formula, right? So this one. So our condition is that she was late. So it's going to be, I'm going to do probability of snooze and late divided by probability of late. We divide out that condition. All right. Well, in part B, we just computed the probability that she was late. That's 0.22. So that's what we're going to be dividing out, right? All right, probability of snooze and late, that's just one of the branches in our table over here. That's this branch, right? So probability of snooze and late, that's my 0.18. And then we'll just go ahead and divide those. So 0.18 divided by 0.22 is 0.82 approximately. So about an 82% chance that if she was late, she hit the snooze bar that morning. Okay. All right, there is another example that I want to do, but it's 9 o'clock and I cannot stand the lag